This section is about limits and continuity. And we're going to start with the definition of a limit like in Calc 1 and kind of compare the two, but we're going to take this limit here and look at the definition. It says, let f be a function of two variables whose domain D includes points arbitrarily close to AB. And we say the limit of f of xy as xy approaches AB of f of xy is L. That's this definition right here. And we write it accordingly. Now, if you look down below, there's two other ways to write it. I don't think I've ever seen the first one. And the second one is just not as well done. So we're going to use this limit notation circled in black. If we compare that to the limit notation you learned in Calc 1, we said the limit as x approaches a of f of x equals L. So this one in red is single variable calculus because we have a single independent variable. And the one up here in black is multivariable calculus. You have two independent variables, both x and y. So if you look at the one down here in red, you're looking at a graph and you're following the curve to determine what this value may or may not be defined as. But you're looking for the y value or the height of the graph. And on this one, we're in 3 space. So we're looking for, when we find the value in the xy plane, we're looking for the height of it in z. So it's the same thing, but now we're not sitting on a curve, we're sitting on a surface. We're not even sitting on a plane. I drew a plane, but we're sitting on a surface. So think about all the graphs we looked at in chapter 13. Now this says, I'm going back to our definition, if for every epsilon greater than 0, there's a corresponding number delta greater than 0, such that if we have a point in the domain, xy in the domain, and 0 is less than the square root of x minus a squared plus y minus b squared, which is less than delta. That's your distance formula happening there. Then f of xy minus L is less than epsilon. That's truly your epsilon delta definition of a limit. So limits are not necessarily easy to do. There's a couple different things happening here. In Calc 1, we would always plug in our values first to see if it works. And in Calc 3, we're still going to plug in our values first to see if it works. If you can plug it in and you don't get an undefined value, then you're going to run with that, especially if the domain is all the real numbers in R2. So that works out well. In Calc 2, the limit does not exist if the left-hand limit doesn't equal the right-hand limit. We could see that easily on a graph, especially with like jump discontinuity right here. So you would follow the curve from the left and from the right and determine the left-hand limit doesn't equal the right-hand limit, therefore the limit does not exist. Now in Calc 3, we are sitting on one of these surfaces, so it is not easy. It's not just one way to get to a point like this one. There are lots of paths you could get there. There are lots of the traces you could follow. So we could be going along this trace right here. We could be going along this trace right here. We could be going along some random trace here and here. So in mathematics, in order to prove that something is true, you have to prove it's all true. In order to prove it's false, you just need one counterexample. So to prove it does not exist, we're not going to do this yet, but to prove it does not exist, you either need that the value is different from two different directions. So two different paths, we could say. So you get a different value from two different paths, or you can use the squeeze theorem. Sometimes one is easier than the other, and we're going to look at both. But let's start with the easy case, which is we're going to plug it in to get our values, okay? Our properties of limits are the same extended into multivariables. So we have the sum law, so the limit of a sum is the sum of the limits. We have the difference law, which is similar. We have the constant multiple law, so the limit of a constant times a function is the constant times the limit, so you could pull the constant out of the limit. The product law, the limit of a product is the product of the limits, and similarly for the quotient, provided the limit in the denominator is not 0. So that takes us into looking at a couple of examples. So let's look at this problem. It says find the limit, and it says the limit as xy approaches 3, 2, so we have a very specific point, x squared y to the third minus 4y squared. So we're going to plug these values in for x and y, and we're going to get 3 squared is 9, times 2 squared is 8, minus 4 times 2 squared is 4. So we have 72 minus 16, which is 56. So the limit of this function is 56. Let's look at another one. It says the limit as xy approaches pi over 2. So what we're really looking at is as x approaches pi and as y approaches pi over 2. So if you think about your 3D graph, you're looking at them coming from those ways. We have, there's a fraction here, cosine y minus sine 2y over cosine x cosine 2y. So when we plug these in, we get cosine of y, which is pi over 2, minus sine of 2y, so 2 times pi over 2 is pi, over cosine of x, which is pi, times cosine of 2y, which is 2 times pi over 2, which is pi. Now cosine of pi over 2 is 0, minus sine of pi is 0, over cosine of pi is negative 1, times cosine of pi is negative 1. So we get 0. Now, before we go any further, this top example, number 5, this is called a polynomial function, and it makes sense because it's a polynomial. If you think about polynomials as the sum of the terms, and normally we would do cx to the n, so we do cx to the n, y to the m. So that definitely looks like a polynomial. And then this one is a rational function, number 12. And the rational function, you can find the limit as long as the point you're given is in the domain. So it does not give you an undefined value. So since our pi over 2 gives us a value of 0, then we know that we're okay to go ahead and evaluate the limits accordingly. Now let's go back to the fact that there are some times where the limit does not exist, and we need to show that the limit does not exist. So in Calc 1, we would look at the graph and say the left-hand limit does not equal the right-hand limit because the graph only had a right and a left. But now that we're hitting surfaces and we're talking about paths, we can approach this path from a bunch of different ways, from an infinite number of ways. And you can see this down here. So this pretty picture in figure 3 shows that there can be an infinite number of paths along the surface to get to the same point. So it's not as easy as saying the right-hand limit does not equal the left-hand limit. But mathematically, in order to prove that the limit does not exist, you just need one example of where it does not exist. It's a counterexample of a statement being true. You can't prove by example in mathematics. You have to prove by proving all the cases. But in order to disprove something, you just have to have one counterexample. So what we want to say, instead of saying the right-hand limit doesn't equal the left-hand limit, so if f of xy approaches L1 as xy approaches AB along the path C1, so on our first path on our surface, and f of xy approaches L2 as xy approaches AB along a path C2, our second curve on our surface. If L1 does not equal L2, then the limit does not exist. So you just have to find two paths that are not equal, and that will prove the limit does not exist. Instead of saying the right-hand limit doesn't equal the left-hand limit, we say the limit from C1 does not equal the limit from C2. And it's a similar concept brought forward into multivariable calculus. So let's look at one of these. Okay, so this problem says show that the limit as xy approaches 0, 0 of x squared minus y squared over x squared plus y squared does not exist. They told us the limit does not exist. We just have to prove it. So in order to do that, we need to approach this point 0, 0 from different paths. Let's start this with let's let y equal 0, which means we're pulling this along the x-axis. We're taking our 3D surface and we're reading it along the x-axis at this point. Now we're going to say f of x 0, because we're going to let y equal 0, equals x squared minus 0, which is x squared, over x squared plus 0, which is x squared, so this value is 1. And we say that f of xy approaches 1 as xy approaches 0, 0 along the x-axis. And we don't use the limit notation because we need to be able to specify that it's specifically along the x-axis. So now let's let x equal 0. So we're going to look at the y-axis. This up here would be the x-axis. I forgot to fill that in. Then we're going to say f of 0y equals, when we plug 0 in for x, we get negative y squared over positive y squared, which is negative 1. So we have f of xy approaches negative 1 as xy approaches 0, 0 along the y-axis. Now you can clearly see that these do not have the same value. And so what we have is as we travel the x-axis, we get a different point than if we travel the y-axis. We're traveling the y-axis this way. So now we say, since we have two different limits, we're going to say since f has two different limits, as xy approaches 0, 0, along two different lines, the limit does not exist. I'm not going to write out does not exist. Neither are you. It's okay. It's all good. In this example, f of xy equals xy over x squared plus y squared. We're supposed to show that this limit does not exist. So let's talk about the easy way to do it that we did last time. Let's let y equals 0. So this is, we're going to travel along the x-axis. So when we do, we have f of x 0 equals 0 over x plus 0, and 0 over anything is 0. And then let's look at the y-axis. We're going to say let x equal 0. So we have the y, we're traveling the y-axis here. So we have a 0 comma y, and we get 0 over 0 plus y, which is 0. But the limit does not exist. So that means we need to look at a different path. That's not helpful here. Let's let x equal y. So this is the identity plane. This is not a line, this is a plane. So we're just going to say x equals y. Now, when we do that, we're going to say f of x comma x. Instead of f of xy, we have f of x, x. So we have x times y, which is x squared over x squared plus x squared. So we have x squared over 2x squared, which is 1/2. Now we have different values traveling different paths. And these two up here weren't helpful because we're on different paths. And the question is, how can this exist? Well, you got to remember a surface is happening here. So this must be an interesting shape. So we picked one more line to check. And now we can say that since we have two different limits, let's say since limit 1 does not equal limit 2, then the limit does not exist. Then the limit xy approaches 0, 0 of xy over x squared plus y squared does not exist. You can see there's an interesting thing happening here at the origin of this graph. So the x and y being 0 in here. So that's why it didn't really pair up for you to use x and y. You got the same value, but that doesn't guarantee that the limit is at 0. We're going to get into that more later, but right now, just try a different line. The line y equals x is a good line in this case. You should start every limit with evaluating. So if we evaluate this, we put in 0, 0, we end up with 0 over 0. And we want to say L'Hopital's rule, which is beautiful in single variable calculus. But we are not there yet with multivariable calculus. So we're going to look at the different paths. So let's let y equals 0 and travel the x-axis. So if we do that, we're going to say f of x comma 0 equals 0 on top, because 0 times anything is 0. And we have x squared on the bottom, which is 0. Beautiful. Can we say that when we let x equal 0 for the y-axis, we have the same thing? So can you see that we're not getting a different result? So I don't feel the need to work it out. Let's let y be replaced by x. So f of x gives me x times x squared, which is x to the third, over x squared plus x to the fourth. So we have x to the third over x squared plus x to the fourth. Now we can cancel the x squared with all of that, so we get x over 1 plus x squared. So when you plug in 0, 0, we get 0 over 1, which is 0. And that gave us same result, so we haven't found a different path yet. We're going to switch it up, and I'm going to explain to you where this came from in just a few minutes. But let's go ahead and say let x be replaced with y squared. So we're going to say f of y squared y equals y squared times y squared is y to the fourth. And then x squared would be y squared squared plus y to the fourth. So that gives me y to the fourth over y to the fourth, which is 2y to the fourth. So we get 1/2. Notice our different results, finally. Now the reason I picked x squared, let's go back up here. If I replace the x squared with y squared, that's going to give me a common denominator here, and it's going to give me all y's in the numerator. So that's going to work out nicely and easily for me to handle. So hopefully you can see why we chose y squared for x. It helped give us our different result. Therefore, and if you don't know this yet, the 3 dots mean therefore. We're going to say the limit does not exist. Since I'm going to say L1 does not equal L2. I hope this example makes sense to you. The second way to prove a limit does or does not exist is the squeeze theorem. Let me remind you of the Calc 1 version of the squeeze theorem. It says if f of x is less than or equal to g of x, which is less than or equal to h of x, and if the limit as x approaches a of f of x equals the limit as x approaches a of h of x, which equals some value L, then since g is squeezed by f and h, we say the limit as x approaches a of g of x has to equal that same value L. So look at this problem. It says find the limit as xy approaches 0, 0 of 3x squared y over x squared plus y squared if it exists. Now, if we were to trace it along the x-axis headed to the origin, we would get 0. If we were to trace it along the y-axis headed to the origin, we would get 0. So that would be the x-axis when y equals 0, and the y-axis when x equals 0. And if we let y be x squared, and if we let x be y squared, we get 0 for all of them. So we tend to suspect and think that maybe the limit exists and it's going to be equal to 0, but we have to show it. You can't just hope and pray and say the limit is 0. So we're going to use the squeeze theorem. We're going to choose f, the function f, and the function h accordingly so that g is between them, and hopefully we can do it pretty easily. To choose your squeeze theorem, you have to be creative and think about it, but you learned a lot of that in Calc 2, so hopefully that's not too bad. Let's consider the denominator. The denominator x squared plus y squared. Let's say that it is greater than or equal to, we could choose x or y, but let's choose x. Let's choose x squared because we have an x squared in the top. So I'd like you to be able to think about and see where this is coming from, but because we have an x squared in the top, we know that we want to kind of compare these values. So let's say note that x squared is less than or equal to x squared plus y squared. That makes sense. we could also say since y squared is greater than or equal to 0, and it has to be because it's positive. Now, because this is true, we can say that x squared over x squared plus y squared is a value which is going to be less than or equal to 1. It is a proper fraction. Since y squared is greater than or equal to 0, I either have x squared over x squared or x squared over x squared plus a number. So this is going to be less than or equal to 1. Then we're going to take this crazy fraction here, 3. I'm going to rewrite it to say y times x squared over x squared plus y squared, so you can see exactly what's going on here. Now, this part in blue, let's rewrite it with blue on it, so you can see that's the part over there. So we know this part is less than 1. So this all has to be less than or equal to 1 if y is positive. So let's put absolute value bars around the whole thing, and we're going to say it's less than or equal to 3y times 1, which we know to be true because 3y times 1 is 3y. So I'm going to scroll a little bit here. And then we could move these absolute value bars up here to say the absolute value of 3y here. And the 3 is not even necessary, times x squared over x squared plus y squared is less than or equal to the absolute value of 3y. You can see that to be true right now. So let's say that we could then say that 3x squared y, the original function, over x squared plus y squared is less than or equal to 3 times the absolute value of y. So if y is negative, that is true, and if y is positive, that is true. And then to create our squeeze theorem, we need another function on this side. Let's make it the same function, 3 times the negative 3 times the absolute value of y. So here we have our squeeze theorem. If we go back and look at the squeeze theorem, we have f and we have h with g in the middle, and that is a true statement here. Now, if we consider the fact that when y, the absolute value of y approaches 0, then y approaches 0. So that means that the limit as xy approaches 0, 0 of negative 3 absolute value of y equals 0, and the limit as xy approaches 0, 0 of 3 absolute value of y equals 0. So by the squeeze theorem, therefore, by the squeeze theorem, the limit as xy approaches 0, 0 of our original function, 3x squared y over x squared plus y squared, has to equal 0 as well. Remember that if the limit of f of x equals limit of h of x, and it's the same value, then since g is in between them, it has the same value. So hopefully the squeeze theorem makes sense. So let's talk about continuity. A function of two variables f is called continuous at the interval ab if the limit as xy of xy approaches ab of f of xy equals f of ab. So back in Calc 1, we would say that a function is continuous if there were no breaks, no holes. So this would be discontinuity here. But if you could draw it with no breaks, no holes, it was continuous. And that was because the limit as x approaches a of f of x equals f of a. So the value has to equal the limit. And if you looked at it, it would be a graph, and like this would be at the value a, f of a. So then if the value is equal to the limit, then the graph is continuous if that's true over the entire interval. And that's what this same thing is saying. If the value at that function at that xy point is equal to the limit, then you have continuity. We say down here that f is continuous on D if f is continuous at every point in the interval a, b, and d. So what we're saying is the surface, in 2D we talked about a curve, and in 3D we're talking about a surface. And the surface is continuous if it has no hole or break, just like we talked about for a curve in Calc 1. So let's look at a few examples. The question is, where are the following functions continuous? So this first one, f of xy equals x squared minus y squared over x squared plus y squared. So if you look at this function and our discontinuity, one of the places we find it is when the denominator is equal to 0. So if we set this denominator equal to 0, the point 0, 0 makes it discontinuous because it's not defined at 0, 0. Since we have a rational function here, the domain of the top is all real numbers, so it's everything in R2. And the domain of the bottom is xy not equal to the point 0, 0. So our domain overall would be the domain is the set of xy such that xy does not equal 0, 0, because that's where we have our discontinuity. I'm not sure how WebAssign is going to ask you for that. They probably don't ask you for the set notation. They'll probably ask you how is it discontinuous. Let's look at another example. Same question. And the question is, where is the following function continuous? Oh, that's why we answered this accordingly, because it's continuous everywhere except 0, 0. So look at this example. We're going to say g of xy. It's very similar to the last one. It says it's a piecewise function, x squared minus y squared over x squared plus y squared if xy does not equal 0, and 0 if xy equals 0, 0. Now, if you think about your piecewise functions, what they've done is they've taken out the discontinuity, possibly because we have a 0 here, and the top part of the piecewise function is only discontinuous at 0, 0. So we've defined the problem is define the piecewise function at 0, 0. So then we need to think about our definition. So we have the limit of f of x, the limit as xy approaches 0, 0 of g of xy. I'm not going to write it all out. And we get that this limit does not exist because we did this problem earlier in the video. But we know that g of 0, 0 equals 0. Since these two things are not equal, then we are discontinuous at 0, 0. Based on the definition in the previous screen, remember that the value of the function has to be equal to the limit of the function at that point, and it's not true in this statement. Therefore, we still have discontinuity at 0, 0, even though that we have a piecewise function that's defined at 0, 0. For the next example, we're going to look at another one that we've already done. I know it's nice that way, right? Too bad your homework doesn't go that way. I understand. So the equation is 3x squared y over x squared plus y squared. Now you remember doing this a few minutes ago. And it says if f of xy is not equal to 0, 0. Now the reason that happens is if you pause right here and think about this, in your denominator, again, x squared plus y squared can't equal 0. So we have discontinuity at 0, 0. So the piecewise function is often used to make a graph continuous, hopefully. We saw that that failed in the previous example because it's still discontinuous up here. So let's check this one out. So they define the piecewise function to be 0 if xy equals 0, 0. So go back in the video if you need to and look at it. But we know that we found the, let's move this up just a little bit. So we found the limit as xy approaches 0, 0 of 3x squared y over x squared plus y squared to be 0 by the squeeze theorem. Now, if you look, that's actually equal to f of xy at 0, 0. So yes, we have continuity here. So this graph is continuous. This graph is continuous for all real numbers in the 2 space. Continuous on R2. Up here we should have said, let me go back to the previous one, discontinuous at 0, 0. I should have written it in. So this one is continuous on R2. The next example says Again, where's the function continuous? And we're going to say h of xy equals e to the negative parentheses x squared plus y squared. And so what we have here is we have a composite function. So if you think about a composite function, you consider the derivative of the inside function and the derivative of the outside function when you think about inside and outside functions for composite functions. Let's split up this composite function. Let's let g of xy be equal to x squared plus y squared. And then let's let f of t be e to the minus t. So we've got the parametric equations going on. So then if you consider f of g of xy, then we put it all together and say e to the negative g, which is x squared plus y squared. So it breaks about pretty nicely. But when you look at that, the composite function, the domain of the inside function is all real numbers on R2, and the domain of e to the minus t is all real numbers. It's continuous for all values of t. So this is all real numbers on t. So the domain here is all real numbers on R2 because the domain is not restricted anywhere. So the next example says, where's the function h of xy equal to arctan y over x continuous? Again, let's split up this composite function. So I'm going to say g of xy equals y over x, and f of t equals arctan of t. I don't usually write arctan. I don't think very many people do. Let's call it inverse tan and write it that way. So we have inverse tangent of t, and I prefer that notation, so I'm going to run with it. Now, the domain here is x cannot equal 0. So let's say our domain here is x cannot equal 0, and this graph is continuous everywhere. The arctangent graph is continuous everywhere. So when you put these two together, our domain of this composite function is going to be everywhere except x equals 0. So we just say x cannot equal 0 for our domain. And we can see this in the graph. The graph in this figure shows the break in the graph of h above the y-axis. So you can see that we don't have x equal to 0. Now, everything we've done in this section, we can extend to 3 or more variables because we're in multivariable calculus. Now, that means 3 or more independent variables. So we've done the limit as xy approaches 0, 0 of f of xy. So we could extend that to say the limit of xyz approaching 0, 0, 0 of f of xyz, or even more. And we can find that limit to be L maybe, or does not exist. So we're looking at it in 3 spaces instead of just 2. And then we can look at continuous functions. So continuity, a graph would be continuous if the limit of x, y, z approaching ABC of f of x, y, z has to equal the value of f of x, y, z. So it just moves it up a step, and you can see that that's true. An example that we could look at here is consider the function f of x, y, z equals 1 over x squared plus y squared plus z squared minus 1. Now, the question is, where is it continuous? And we know that the denominator cannot be equal to 0. So x squared plus y squared plus z squared cannot equal 1. That's when our graph would be discontinuous. So it's continuous at every other point in R3. Notice we have 3 independent variables. So we're considering R3 for our domain. So it's discontinuous at every point in the sphere. This is a sphere with a radius of 1. So we would say we are continuous. The question was continuous. That's what I paused for. We're continuous on R3 except x squared plus y squared plus z squared equal to 1. And they have the definition of the limit defined to be in space. And I think that you can travel through that. So I think this will handle all of the questions you have about your homework. Hope you understand and enjoy this lesson.